Okay, so number one. Number one is just going all the way back to chapter 1 when we first learned about limits. So I'm trying to evaluate the limit of this rational function here as x approaches 1. And what's a great way to start any sort of limit problem?
Probably factoring out the...
Even before that. Plug it in. Plug 1 in, see what happens. If I plug 1 in, I get, what is that? 1 plus 3 minus 4 over 1 minus 1. I just get 0 over 0. Okay? Which, of course, we know is an indeterminate form, meaning doesn't tell me anything. So I've got to manipulate this equation somehow in order to get a meaningful result. How am I going to do that? Mona already mentioned factoring, right? In this case, I can just factor. What is that? Denominator factor to? That's my easier, more easy, the easier one to factor, because that's just a difference of squares. So we get x plus 1 over x minus 1. Notice which of these factors is my discontinuity, is causing the discontinuity.
X minus 1.
Yeah, so theoretically, what do I want to be able to factor out of that numerator?
X plus 1.
An x minus 1, right. I want to be able to factor an x minus 1. So sure enough, that can kind of give you a hint of how it factors. I know I should be able to factor out an x minus 1, and therefore my other term is going to be x plus 4. And you can double check that by multiplying that through, right? 4 times negative 1 gives you that minus 4, and 4 plus negative 1 gives you the plus 3x. Very nice. Well, that's awesome because now those x minus 1 terms cancel, and that tells me that this limit is equivalent to this limit of just x plus 4 over x plus 1. Now what do?
Plug in 1.
Now I plug in the 1 again, and now I don't get an indeterminate form. I get 5 over 2, and that's my answer. Right? Now I can plug that 1 in for x. Awesome. Any questions about that one? Good little review on limits. What do we call this type of discontinuity? Which type is it? Yeah, it's a removable discontinuity because we were able to cancel out that discontinuity and evaluate the integral or evaluate the limit. I still had a result for the limit, even though I didn't specify direction or anything like that. Right, that's a removable discontinuity. Okay, oh boy, if I start asking questions like that, we'll never get through them. Okay, question 2. This one's talking about your difference quotient. Okay, so here's a function, negative 3x squared minus 2x minus 2. And it wants me to calculate the difference quotient for this function. So let's remember my difference quotient. What does the difference quotient look like? It's that whole f of x plus h minus f of x over h. Why was the difference quotient important again? Where did we use it? Where did we end up using it? Derivatives, right? That's how we first calculated derivatives. We used the difference quotient because the difference quotient is calculating a rate of change. It calculates an average rate of change, and then we let h approach 0 to make it an instantaneous rate of change. So that's why difference quotients were important, is because it's how we first calculated derivatives. So now that I have my difference, now that I know my difference quotient formula, I can go ahead and kind of use this. So first I'm going to take my function, but plug in x plus h. What does that give me? That gives me negative 3 times x plus h squared minus 2 times x plus h minus 2. So that right there is my f of x plus h. Minus, and then just my function. All over h. Everybody okay with that so far? Now, of course, there's a lot more I can do with this. And in fact, what do we expect to happen? When I simplify this out, what did we notice with my difference quotient? What should I be able to do by the time I'm done?
We get it down to just H. H's, I should say.
That's if we were, that's if we had a specific x value we were evaluating it at. In this case, we don't have a specific x value. So we're not going to be able to get it down to just h's. Well, let's keep going, see what happens. So if I expand that numerator, I get negative 3x squared minus 6xh minus 3h squared minus 2x minus 2h minus 2 plus 3x squared plus 2x plus 2. Everybody okay with that? These all became addition because I'm subtracting a negative. Right? I was subtracting negatives in each of these cases, so they all became addition. What do we notice?
Some things cross out.
Yeah, I have a few terms to cancel. Negative 3x squared and positive 3x squared. Negative 2x, positive 2x. Negative 2, positive 2. What terms cancel out? Everything that didn't have an h. So everything that didn't have an h in it canceled out, leaving me with a whole bunch of terms in the numerator that all have an h in it. Meaning, what can I do now?
Factor out an H.
Factor out an h. Right, this was something that always happened when I used difference quotients. You were always able to cancel out everything that didn't have an h so that you can factor out an h. Why is it important to factor out an h? Cancels with the 1 in the denominator. And so I'm left with negative 6x minus 3h minus 2. Very nice. Cool. Any questions about this one? About using that difference quotient? Yeah, Stockton.
Can you, I don't know why, can you show me the math on negative 6 xh? Like in the,
Yeah. So that's just this term right here,
yeah.
the x plus h squared. So if I come do that over on the side, if I do x plus h times x plus h, you'll get x squared plus xh plus h times x. Well, hx and xh are the same, right?
Yeah.
Multiplication, you can switch the order around. So that's another xh plus h squared. So you're left with x squared plus 2xh plus h squared. And then when you multiply it by that coefficient of negative 3, you get the negative 6xh. Okay, cool. Other questions? You good? Okay. Number 3, very nice. Okay, so now we get into actual derivatives, okay? And, you know, I think when we first talked about derivatives, we did it all using the difference quotient, and then we learned all these shortcuts. Well, now you guys know all the derivative rules, so don't stress about, oh, do I use the difference quotient? Do I just use your derivative rules, okay? So, for example, with this one, you've got y equals x squared minus 2x plus 5 over x squared plus 7, and I want to find y prime. I want to find the derivative. So what am I going to use?
Quotient rule.
Quotient rule. Yeah. That's my shortcut if I have a function over a function. So that's what I'm going to use here. I'm going to use quotient rule. Okay. Quotient rule is if you're taking the derivative of a function over another function. This is how you'll see it in your formula sheet. You take your denominator, multiply it by the derivative of the numerator, minus, and then you switch those. Numerator times the derivative of your denominator, and this is all over the denominator squared. Okay. So I'll go ahead and put that together here. So I'm going to have the denominator multiplied by the derivative of the numerator. What's the derivative of the numerator? 2x minus 2, right? Derivative of 5 just goes to 0, right? Because it's a constant. So 2x minus 2 minus numerator, x squared minus 2x plus 5, times the derivative of the denominator, which is just 2x. Very nice. All over that denominator squared. Awesome. Now, if you remember, the way Pearson works is if you just plug it in like that, it should go ahead and give you credit. But in case you're curious.
So it counts for the fun too, yeah?
But if you simplify that numerator, it does simplify kind of nicely. 2x squared plus 4x minus 14 over x squared plus 7 squared. In case you're curious. Any questions about this one? Good little review of quotient rule, how that works, and as well as kind of a quick review of derivatives of polynomials. Right. We'll move on then. Okay, number 4, we've got a function 2x to the 6th minus 10x cubed plus 7x. And I want to find this crazy thing. What is that asking for? You guys remember? Fifth derivative, right. So this is all about higher order derivatives. Can you find the fifth derivative of this function? Okay. Well, I can do all the work for it. It wouldn't be too bad, but I can also think through this a little bit. Tell me about this term. What happens when I take the derivative of this term?
It's just going to cancel out.
It becomes a constant, and then if I take the derivative again, it goes to 0. So that term is just going to go to 0 if I take multiple derivatives. What about the next term? So that one's going to go to 0. This term? Yeah. After 3 derivatives, it becomes a constant, right? So then what about after 4 derivatives?
0.
Also goes to 0. So that's also going to go to 0 after 4 derivatives. This one's only after 2 derivatives. So the only term I really need to worry about is this highest power term. Okay? So let's see what happens as I take the derivative of that. So y prime is equal to 12x to the 5th. And technically, right, if we want to think about those other terms, we already know they're going to go to 0. But if I wanted to think about them, I'm going to have minus 30x squared plus 7. Second derivative, I'm going to get 60x to the 4th minus 60x. And then sure enough, that 7, by the second derivative, that 7's gone to 0 now. Okay, keep going. Third derivative, 60 times 4 is 240. X to the 3rd minus 60. Oh, that's the third derivative. And now that I'm on the fourth derivative, you'll notice that now I'm left with just that first term. Oh, what is that? What is that? 720? So sure enough, this that first term is the one that is the only one that's really stuck around all the way down to. We've finally done it. We've reached the fifth derivative, and I have 1440x. So there's my fifth derivative, 1440x. Cool. Any questions about this one? You're just taking the derivative over and over again. Too bad. Okay. Okie doke. Number 5. Aha! So this one's sketching a graph. And it gives me a bunch of information here. So let's look at all this information. And I'm going to organize it a little bit differently than they have it because I think it's helpful. But it tells me, first off, it tells me this. Of course, it tells you more, but we're just going to focus on these first. Because all of this information is based off of the x value of -3. Okay, so all of this is telling me about the x value of negative 3. And let's look at each piece of this. First off, what does this tell me?
But it means when you input -3 as an x value, you get 1 as an output.
Okay, so it just tells me, right, my corresponding output for negative 3. This tells me what my y value is at negative 3. So that's all this one tells me. This just tells me the y value. Okay. Or you can think about it as like, this is a coordinate point, negative 3, 1. Okay. Okay, now, what about this one? What does that tell me?
That one that's in terms of speed terms, it would be acceleration.
Yeah, it's acceleration. If I'm thinking about it in terms of position and speed, it's acceleration. It's the second derivative. What does the second derivative tell me about? Concavity. So this is telling me about the concavity of my function, specifically that it's... Oh, no. Oh, there we go. Specifically that it's concave. It's less than 0. Down.
Concave down.
It's concave down. Very nice. So I know that I'm concave down at negative 3. Okay, what does this last thing tell me? Hmm? Yeah, I'm talking about my rate of change. Rate of change is 0. Darius? I have a what? My slope is 0 at negative 3. Very nice, right? So my slope is flattening out at negative 3, meaning I have a critical point, right? So this is telling me that I have a critical point at negative 3. And critical points are important because what happens at critical points? What can I potentially have at critical points?
Local min or max.
Right, a local min or max. So this tells me I have a potential local min or local max at negative 3, but I'm concave down, meaning that it has to be a max. It has to be a local max. Very nice. So put it all together. I'm working with a local max. Oh, goodness. Local max of negative 1 at x equals negative 3. Not negative 1, sorry, positive 1. Positive 1. So I have a local max of 1 at x equals negative 3. Everybody okay with that? Very nice. So let's look at the next information they give us. So after that, it tells me that, let's see, f prime of 1 is equal to 0, f double prime of 1 is greater than 0, and f of 1 is equal to negative 5. So, in a similar way, I can summarize all of this information by saying what? What conclusion can I make about x equals 1? What do I know about x equals 1? I gotta speed up. I'm only on number 5. Oh no, we started at 130, right?
Yeah.
Oh yeah, we're doing it. We're doing it. What conclusion can I make?
It's a local minimum.
It's a local minimum. Right. It's a local minimum of negative 5 at x equals 1. Right? It's a critical point because the derivative is 0. Right? Underline as I talk about this. It's a critical point because the derivative is equal to 0. It's concave up, telling me it's a local minimum. And then, of course, the last one just tells me what the y value is. Okay? So at this point, it gives you more information, and the last information it gives you is just concerning like where the inflection point is. But at this point, you can go ahead and graph your function. Because now what am I looking for? I'm looking for x is, I'm looking at two critical points at these two x values, right? I'm looking for a local max at -3 and a local minimum at at +1. The maximum is at 1, and the minimum is down at -5. So that's what my function looks like. Any questions about this one? Okay. Awesome. Okay, so this is number 5. We're now on to chapter 2, because this one's talking about how derivatives affect the shape of the graph, which was a big thing in chapter 2. Okay, but that leads us to optimization. Okay, so 6 is where we get into our optimization problems. So 6 is, we've got this going on. And then this is my y value. Okay. So I'm creating a pen, a rectangular pen. Well, I guess 3 rectangular pens right next to each other where you're sharing fencing for each of these pens. And we're told that we have 976 yards of fencing. Okay. And we want to find the maximum area. This is not a question. I'll get rid of that. So find the maximum area. Okay. This counts as optimization because we're trying to optimize the amount of area that we have. Okay. So what do we do?
We write down equations.
Equations, right? I need equations. And specifically, this is a good thing to keep in mind with any of these optimization problems. If I want to optimize area, right? If I'm trying to find maximum area, if I'm trying to optimize area,
To do a square.
well, usually, yeah. But the fencing in the middle is going to throw that off a little bit. But if I want to optimize area, if I want to optimize something, I need an equation for that something. So in this case, if I want to optimize area, I need an equation. Oopsies. I need an equation for that area. In this case, if I'm maximizing, I think, total area, if I'm maximizing total area because I'm talking about total fencing, what's my area formula? X times Y. So, great way to start. If I want to optimize area, I need to write an area equation. Now what?
Perimeter would be, you have to worry about the perimeter of the.
Okay, the perimeter is an important piece here. Why do I need to worry about the perimeter? Well, first of all, if I tried to take the derivative right now, I have 2 different variables that I'm worrying about. And so, therefore, and since these are, and I guess kind of related to this now that we've learned about chapter 6, where, hey, it's okay to have 2 different independent variables. The fact that I have a limited amount of fencing, what does that tell me about my 2 variables?
They're limited.
They're no longer independent. They depend on each other because of that limited amount of fencing. Are we okay with that? So these aren't independent variables anymore. Which means I should be able to get it all in terms of only 1 variable. And that's what I'm going to use the fencing for. So help me out with this fencing. What do I do with that?
The equation for the perimeter of the fencing
Mhm.
would be 2x plus 4y.
Right. 2x plus 4y. Right? 2x because you have one of these sides and one of these sides. And 4y because you have 1, 2, 3, 4 of those sides. Awesome. So there's my perimeter equation, and that is equal to 976. All right. What do I do with that? Solve for one of the variables. Solve for one of the variables. And what this does is shows how they depend on each other. So if you solve for x, you get 488 minus 2y. And this shows how x depends on y. Because, like we said earlier, x and y are no longer independent. They depend on each other. Okay. What do I do with that? Plug that into my area equation. I have no idea why these red boxes randomly show up.
It thinks you're trying to write letters or something.
Oh, maybe. But still, I'm not using this thing, the little quick type thing.
The latest update of the Note app has automatic AI in that.
Oh, stinking automatic AI. Okay, we're getting sidetracked. Okay, so I've plugged this in for x. I've simplified a little bit. Now it's completely in terms of y. It's only in terms of one variable. Now what do? What comes next? I've got my area just in terms of y. This next step kind of boils down to, what does this have? Why is this in my calculus class? Because
Separate out a line or hold on.
well, yeah, it comes back to the question of what are we doing? Why are we doing this in a calculus class? Because we use derivatives. We're going to use derivatives to actually help me optimize, because derivatives can help me find where I have minimums and maximums. How? Finding the critical points, which is where the derivative is equal to 0. So what do I do next? Now that I have my area function, I'm going to take the derivative. Here, in fact, I'll bring it down here. I'm going to take the derivative of that function. So 488 minus 4y, and set it equal to 0. Because I want to know where that function is flattening out. Where is it reaching its peaks or valleys? And then I can solve for y. So I get 488 is equal to 4y, and therefore y is equal to 122 yards. Since it's my only critical point, I can go and assume that this is going to give me my maximum. Okay. And then I can solve for x. I can solve for x by just using this equation. X is equal to, oops, sorry, no. I don't need that parentheses. X is equal to 488 minus 2 times 122, and you get 244. Awesome. Okay. Perfect. Any questions about this one? Okay. Okay. Number 7. Let me just make sure I don't skip anything. Okay, number 7. Another optimization problem, but this one's going to look a little bit different, because this one, it says, okay, a certain company has a cost equation of 3,500 plus 0.5x squared, and they have a no. Wait, this one's confusing me. Does anybody have it up? Does it give you? So it gives you the cost equation, and then is that a price function? That's a price function. And then it gives you a demand function of 150 minus 0.75x. Yeah, that's right. Okay. Where, and this is like a suit company, so X is number of suits. So if it produces X number of suits, I now have a cost function, and I also have a price function that's going to tell me what price to sell it at if I want to sell that many suits. Okay?
Find the most suitable amount of them.
Yeah, and we're going to find the most suitable number of suits to do in order to optimize. I think we're going to optimize our profit here. So first of all, and I think it walks you through this a little bit, which is nice. First of all, what's my revenue equation? Because in order to optimize, because think about it, if we want to optimize profit, what does profit depend on?
Price and units sold.
And revenue, right? Because that's what revenue depends on, right? It depends on price and units sold. So if I want to maximize profit, I also need to know what the revenue is. What's my revenue equation? How do we commonly calculate revenue? Price times quantity. I'm just going to use that basic revenue equation that we've used before in this class. Price times quantity. But tell me about the price. Depends on the quantity. How? I have an equation for it. Yeah. And it depends in this specific way. 150 minus 0.75x, right? That's my price equation. Tell me about quantity. I used Q up here.
That's our independent variable.
That's our independent variable. That's X, right? That's what X represents. X is your quantity. So I can just do this times X. Very nice. And that's my P of X right there. Okay. So multiply that through, and you get 150x minus 0.75x squared. So that's my revenue equation. Okay, so that's my first stepping stone. And now if I want to maximize profit, going back to what we learned about in number 6, if I want to maximize profit, then I need an equation for profit. So that's part B. So what's my equation for profit? How do you calculate profit again? Revenue minus cost. So I get 150x minus 0.75x squared minus my cost, 3,500 plus 0.5x squared. Okay. Put it all together, and you're left with negative 1.25x squared plus 150x minus 3,500. You okay with that? Because you have negative 0.75x squared minus 0.5x squared, so it becomes more negative. Okay. Okay. And then C is where we get to optimize. So now let's optimize our profit. What number of suits will optimize my profit? So what do? Of which function? The profit function, right. If I want to optimize profit, that's what I'm going to find the critical points of. I'm going to take the derivative of that profit function. So I'm going to take the derivative of my profit function. P prime of x is equal to negative 2.5x plus 150. What do I do with that derivative? Set it equal to 0 and solve. So I'll set it equal to 0 and solve for it. And you get 150 equals 2.5x. And so x is equal to 60. 60 what? Suits, yeah. So you should sell 60 suits in order to optimize your profit. Very nice. And then it keeps going a little bit, and this is just kind of busy work at this point. Now it wants, so what is that optimal profit? D is asking, so if 60 suits optimizes your profit, what is that optimal profit? What does that tell you to do? Yeah, plug 60 into your profit function, and you get negative, not your derivative profit function, it's your profit. So negative 1.25 times 60 squared plus 150 times 60 minus 3,500. Then I think you get $1,000. $1,000. So you get $1,000 worth of profit. And then part E, once again, is just a little more busy work. Is just asking, okay, so if you want to sell 60 suits, what price should you set it at? What is that asking you to do?
The little,
Yeah, plug it into your little p function now. So now I'll plug it into little p, which is just 150 minus 0.75 times 60. And that's just, hello, $105. Cool. So still technically an optimization problem, but what's nice is this one kind of walks you through it and has you find the revenue function in order to find the profit function, and then once you have the profit function, then you're ready to go ahead and take the derivative and set it equal to 0. Awesome. Any questions? Any questions? Any questions? Okay, moving on. What are we on? Number 8. This one will look familiar. So, a university is trying to decide what price to set football ticket. I don't even know if it says football, but set ticket prices for. And here are some things that we know. Well, first of all, we want to maximize revenue. And I'm going to go ahead and say total revenue. Because if you remember, there's a little extra piece of information that we're going to use. Okay, so we're going to maximize total revenue. So, if I want to know total revenue, if I want to maximize total revenue, what am I going to need an equation for? Total revenue. So I want to create a total revenue equation here. But if we read this problem carefully, what does this total revenue depend on?
the concession price, the ticket price,
It depends on both concessions and
the ticket price.
attendance, right? How much attendance and concessions. So let's start with attendance. How do you calculate attendance revenue? Revenue from attendance? Yeah, the price of your ticket times your attendance. Okay? What about concessions? In my problem, it tells me that we're earning $5 in concessions per person. So, concessions? 5 times whatever your attendance is. Very nice. So, to move on, I need to get this all in terms of just one variable x. In order for me to take the derivative, I need this all in terms of x. And so what do we want x to be? I think, actually, sorry. Yeah, we want x to be the ticket price. How do we know that? Because in the problem, it says, what price should you set your ticket to optimize your revenue? So we want that independent variable to be ticket price. So instead of changing it to x, I'll just keep it as little p. So that means we need to figure out how a depends on p. How does a depend on p? And this was that extra information that it tells me. So, what else is it telling me? It tells me that when the price was $16, the attendance was 40,000. Okay, so that's one thing it tells me. And of course, your problem is going to be slightly different, but the same principles are true here as I go through this one. Okay. So it tells me that. It tells me $16, the attendance was $40,000. And then it also tells me that if I decrease the price by $2, the attendance goes up by 10,000. Okay? Well, I can show that by just continuing my table. If I move my price down to $14, my attendance goes up to 50,000. And so on and so forth. That pattern, we're going to assume that pattern continues. So we have that pattern. Yes. Uh-huh. Yeah. We're not going to worry about the infinite cases. Okay. So, how does A depend on P? Well, take a look at this table. What type of relationship is this? It's linear. So this is a linear relationship. Which means I should be able to solve for the slope. Okay? What's my slope? Remember, we want P to be my independent variable. So we'll go ahead and treat this as my X. This is my X, this is my Y. So what's my slope? Other way around. Remember, we're treating the A as my Y. So change in Y over change in X. So change in attendance over change in price. So 10,000 over -2. -2. Yeah, it's important that this ends up being a negative slope. So I get -5,000. So there's my slope. Okay. And so now, to create my equation, I can go a couple different ways from here, depending on what's easier for you. I could just keep going with my table until I get to, hey, what's the attendance at a price of 0? You can just keep going that way. Or you could use point slope form, if you remember point slope form. Or I could solve for what my y-intercept is. So I could say, okay, y is equal to negative 5,000 x. Oh, sorry. We're not working with y and x, are we? We're working with a and p. So a is equal to negative 5,000 p, right? Your slope times your independent variable, plus some y-intercept. How do I figure out that y-intercept? I can just plug in one of my data points. Plug in one of my data points. So 40,000 equals negative 5,000 times p, which is 16, plus b. And by doing this, you can solve for it. Because what is negative 5,000 times 16 is 80,000. This is, oh goodness. This is 40,000. Negative 5,000 times 16 is 80,000, negative 80,000. And so when you add that over, you get 120,000 equals b. And there's your slope or there's your y-intercept. And so now I have a linear equation that relates A to P, that shows how A depends on P. Any questions on how that process worked? How I got those things. Hopefully now that you kind of see that done, you can relate that to the numbers that you're going to have on your problem. Okay. Cool. So now that I know what A is equal to, I can plug that in. So I get P times negative 5,000 P plus 120,000. Sorry, that looks like an 8, but it's a 5. Plus 5 times negative 5,000 P plus 120,000. Okay. And that gives you, after you multiply everything through and simplify, you get negative 5,000 P squared plus 95,000 P plus 600,000. So far, all of this work has just been to get me my revenue equation completely in terms of the price. So now I have revenue completely in terms of price. Now what? Now I'm ready to take the derivative and set equals 0, right? Now I'm ready to look for those critical points by taking the derivative and setting equal to 0. So the derivative of this revenue equation is negative 10,000p plus 95,000. If I set that equal to 0, I get p is equal to 9.5. So, very nice. There's my optimized price. That's the price that I should set it at. And if I set it at that price, if I calculate the attendance at 9.5, I get 72,500. Sorry, I changed my notation. We were using lowercase a. Okay. Awesome. Any questions about this one? Okay. Very nice. So, 3 different optimization problems. Yeah. Good chance you might see one of those on the test. Okay. Let's keep going though. Number 10. No, not number 10. Number 9. Whoa. Whew. Okay. Number 9. So, this one. Oh yeah, this is one where it's like a demand equation where you've got P representing the price, X is the number of sales. But what are we assuming about both of these things?
They're both positive.
Right, yeah, fair enough. We don't want to be dealing with negative prices or negative sales. But in this problem specifically, number 9, we're assuming something special about both of these.
They're both,
We're gonna assume that both of these depend on time. This problem is from 2.8, where we talked about implicit differentiation, when you take a derivative of a function in terms of a different variable. Okay, so let's see. It gives me the following function. It gives me 5p plus 5x plus 3px equals 99. And it wants me to find the rate of change of x. Okay, but that's interesting because how do I find the rate of change of x when that's my independent variable, right? Well, the difference here is that, once again, we're assuming that x depends on time, that we're not going to be producing the same amount of stuff all the time. We're changing how much we produce depending on what, I don't know if this is seasonal or weekly, depending on what day of the week it is, but x is changing in regards to time. So what are we finding? We're finding how is x changing as t changes. We're finding the derivative of x in terms of t. Which means, what do I want to do with this whole function right here? Not necessarily get it in terms of t. I want to take the derivative in terms of t. I'm going to take the derivative of all of this in terms of t. By the way, it also gives me some more information that I didn't list, so let's list that real quick. We're going to look specifically when p is equal to 6, when x is equal to 3, and when the price is changing by 1.3. So notice it gives me dp over dt, which represents how is the price changing in terms of time. So I'm going to take the derivative of this whole function in terms of t. So let's break it down each piece, right? One of my derivative rules is you can separate it by addition or subtraction and focus on each of the different terms. Okay, so tell me about this piece. First one. What's the derivative of 5p? Normally, if I were taking this derivative in terms of p, what would my derivative be? Just 5. But because I'm taking this in terms of t and not p, I'm then going to multiply that derivative by what? Right, dp over dt, or p prime. So we used p prime, or you could think about it as, we've used p prime before, or you could write dp over dt. Riley's just skipping to the step where we go ahead and plug in 1.3. Okay. Next term.
We need that derivative for x. It's 5.
Yeah, it's going to be very similar, where my normal derivative is 5, but because I'm taking the derivative in terms of t, I'm going to multiply this by dx over dt, or x prime. So here, I'll put these in kind of parentheses down here. This is dp over dt, and this is dx over dt. Okay? Next term, 3px. How do I take the derivative of that? Yeah, this one's tricky. What are we assuming about p and x? They're both, yeah, fair. They have that shared coefficient of 3. What are we assuming about p and x, though? They're both functions of time. Therefore, what do I need to use? Product rule. I need to use product rule here. Because both p and x, they're both functions. So I need to use product rule. Okay, so, and when you use product rule, there's a couple different ways you can deal with this 3. I can just keep the 3 in front and then multiply my entire product rule by 3 when I'm done. Or you can put the 3 with the p and do it that way. Either way works. I usually like to just assign the 3 to that first function and do it that way. So product rule tells me I'm going to keep the first function, multiply by the derivative of the second function. What's the derivative of x? X prime. Okay. Plus, now I'm going to do the opposite. What's the derivative of 3p? 3 times p prime. And then multiply it by my second function, which is just x. Very nice. And that's my product rule. Done. Equals? 0, right. Don't forget, the derivative of 99 is 0. A lot of people forget to take the derivative of that other side. Okay? So the derivative of 99 is 0. Now what do? Now I can start plugging things in, right? Because now I have a function that deals with x, p, x prime, p prime. It deals with all of those things that I'm looking for. So now I can go and start plugging in the values. Okay? So I get 5. Oopsies. Oh, just picking up my finger. 5 times p prime, which is 1.3, right? It's to my dp over dt. Oh, it is AI. Plus 5 times, this is what I don't know. I don't know what dx over dt is. Plus 3p, well, I know what p is, 6, times x prime is once again what I don't know. It's that dx over dt. Plus 3p prime is 1.3. And x is 3. Very nice. Okay. And now if I start multiplying everything, I get 6.5 plus 5 times dx over dt plus 18 dx over dt plus 11.7 equals 0. Combine your like terms and you get 23 dx over dt equals negative 18.2. So I just moved my other terms over to the other side. Divide by 23. And you get negative 0.79. Any questions about any of that? I have a question. Negative 0.79 what? .79 what?
Dollars per unit time.
Not dollars. That's what dP over dt would be, because dP is in terms of price. So it'd be talking about dollars. But what are we talking about with x? Sales. So right. So this is sales, and since this is a derivative, it's a rate. This is sales per. And this last part depends on what time value we're working with. But yeah, we'll go ahead and say, we can say day, or maybe it's in terms of months. I don't know if it might specify in the problem what the t value is, but right, it's sales per whatever the time value is. Sales per day. Cool. Okay. Moving on. Moving on. Ooh, yeah, we got 15 minutes left. Let's see how much we get done here. Okay, we are on number 10, yeah? Yeah, number 10. Awesome. Okay. I'm given a function s of p equals 0.07 p cubed plus 3p squared plus 6p plus 14. And I'm going to use s prime of p to estimate the change in s when the price changes from $18 to $18.10. So this goes back to our section, I think this was 2.6, where we learned about marginals and differentials, where if I wanted to find the exact change, what could I do? To find your exact change, you can just plug in both of these values. Plug in 18, see what you get. Plug in $18.10, see what you get, and then find the difference. Subtract it. Right, and find the difference. But we learned with differentials that you can use derivatives to estimate, because in some cases the derivative might be simpler to calculate than trying to calculate the actual value. So that's what this is asking me to do, is let's use the derivative to estimate the change. And the way we're going to do that is by using these differentials. The change in s, or actually, I think when we talked about it in class, we actually used that delta s. Delta s is approximately the derivative times dP. Okay. And you remember, this comes from that notation of ds over dP is equal to the derivative. Right? Those are just two different ways of notating the derivative. So if you just multiply this over to that side, we get this kind of estimation. Now, so what's my derivative? I get 0.21 p squared plus 6p plus 6 times dP. What's dP in our case? What's dP? P, we're talking about price. dP, change in price. So how much did the price change? 0.1, 10 cents. We're going from $18 to $18.10. So in our case, dP is equal to 0.10, 0.1. So that's what I'll plug in right there. What about P? What do I actually plug in for P? $18. Use the starting value. Yep. So we're going to use the starting value for P. Okay. And just throw that all, we need to start moving faster. So throw all that into your calculator and you get $18.20. No, sorry, that's not a dollar amount. Is it a dollar amount? What does S represent? I don't have the exact thing in front of me. Regardless, you get 18.204. Any questions about this one? So yeah, this is differentials and marginals from 2.6. Okay, moving on. Consider the function f of x equals natural log of x to the 7th minus 8 over x. And let's find f prime of x. Okay, so we get away from the more complex applied problems, and now we just have a nice little simple, hey, let's find the derivative of this. What is this derivative going to require? It's going to require quotient rule, potentially, and chain rule, right? Potentially chain rule and quotient rule. So, it doesn't make for a very fun derivative. It's going to have lots of fractions. Because what's the derivative of natural log of x? 1 over x. So it's going to have lots of fractions involved. Could I potentially make this a little bit simpler? Right?
Use your log rules.
Use my log rules. And I think the log rules are on your formula sheet. So if I have a log, remember natural log counts as a logarithm. If I have the natural log of two functions being divided, what am I allowed to do?
Subtract them. Use separate logs.
Subtract, split it up into two separate logarithms that are subtracted. So I can rewrite this as the natural log of x to the 7th minus 8 minus the natural log of x. Now, if I take the derivative now, it no longer requires quotient rule, which is nice. I don't have to worry about quotient rule. Still need a chain rule for that first one. Because now, do I have any log properties for if I have x to the 7th minus 8 inside of my natural logarithm? No, there's nothing more I can do with that one because it's separated by subtraction. So let's go ahead and take the derivative. Okay, so first one, I need chain rule. So let's take the derivative of the outside function. What's the derivative of my outside function? What's the derivative of natural log? 1 over x. But I'm going to keep the inside function the same. So what do I plug in for x? X to the 7th minus 8. Okay. Now what? Now I multiply by the derivative of the inside function. Derivative of x to the 7th minus 8? 7x to the 6th. Okay. Everybody okay with that? So that's just that first term. That's this one. Okay, what about this one? So now I'll put a little big minus sign. And now derivative of natural log of x? Just 1 over x. Very nice. And I'm done. And that was so much nicer because we didn't have to worry about quotient rule. And we didn't have to worry about fractions inside of other fractions. So nice. So if you remember to use log property, if you see a logarithm, look to see if you can use any of the log properties first before you start taking derivatives or anything like that. Okay. Awesome. Okay. Next one. Ooh. This one yet? No, no. Okay. Number 12. Okay. Here we get into chapter 3, so we're starting to work with exponential functions. So, if you have P of t, this is a percentage of doctors who prescribe a certain medication. So that's what's going on here, and it gives you the function 100, 1 minus e to the negative 0.25t, where t equals months. Okay. This one is also like a multiple part problem. In part A, it asks you, hey, how many doctors will be prescribing this medication after 1 month? What is that asking you to do? Just plug in 1. Yeah. Just plug in 1. And I think in my case, I get like 21%. Well, sorry, let me rephrase that. I get 0.21 something. But because P represents a percentage, I can go ahead and convert that to a percentage. Okay? And then it asks the same question, but after 6 months, which is just P of 6. And I get 0.75 something. Okay? Part B. Part B, it just asked me to find the derivative. So this is good practice of remembering my derivative rules for exponential functions. Okay? So I want to find the derivative. It might be helpful to go ahead and distribute that 100 to both terms. Instead of trying to use some derivative properties or something like that. It might be easier just to rewrite it like this. And then take the derivative. What's the derivative of that first term? 0. So the first term just goes to 0. And then this next term, I'll keep the negative 100. How do I take the derivative of an exponential function like this? Multiply by a constant. What do I do with everything else? Stays the same. So my derivative of this just ends up being negative 0.25 times e to the negative 0.25t. Right? The exponential part stays the exact same, but you just multiply by the constant that was in the exponent. So that gives me negative 100 times negative 0.25.
4.
Yeah, positive 4. No, positive 25. Yeah. Because 0.25 is 1/4. That's where you're getting 4. So what's 1/4 of 100? 25. 25 e to the negative 0.25t. Okay. C. This one's interesting because it has you find the derivative in part B, but then you don't actually use it for any of the future parts. So part C is just asking, hey, how long will it take before 90% of doctors recommend this certain medication or prescribe this medication? So if I'm looking for that, how do I solve that?
0.9 equals...
Right. I'm plugging 0.9 in for P. So I'd have 0.9 equals 100 times... Oh, wait, no. What am I doing? I just realized the reason why this 100's right here is because the function itself is converting everything into a percentage. So forget it. When you do this calculation, you just straight up get 21 and 25. Okay, so instead of plugging in 0.9, I'll just plug in 90. 90 for 90%. And then I'm solving for t, which makes sense because it's asking the question, how many months? Which means t is unknown. So we're going to be solving for t. Okay? Very nice. You'll divide by 100, and notice that's going to give you 0.9. So you get 0.9 is equal to 1 minus e to the negative 0.25t. I'll subtract by 1 and divide by negative, and you get 0.1 is equal to the negative 0.25t. How do you solve something like this? Your t is in the exponent. How am I supposed to isolate t if it's up there in the exponent? Right. How do I get rid of that e? You take the natural log of both sides. So you end up with the natural log of 0.1 equals negative 0.25t. And then you can solve for t. T equals the natural log of 0.1 over negative 0.25, which is about 10. So it only takes about 10 months before 90% of doctors are prescribing. Okay. And then part D asks this question. What's the limit as t approaches infinity of p of t? Well, take a look at this function. I've got just 100 times 1 minus e to the negative 0.25t. Tell me about this piece right here. It's a decay, it's an exponential decay function. So as I let t get infinitely large, this is approaching 0. No, 0. Yeah. What? Oh yeah, right. Yeah, the exponent goes to negative infinity, and e to the negative infinity just is approaching 0. So, right, what happens is that this term will approach 0 as t gets infinitely large. So, in that case, what are you left with? You're just left with that 1. And then 100 times 1 is 100. So what is that telling us? What is part D telling us?
That it's a probability density function.
Ooh, yeah, maybe?
In the sense that I guess it's
No, I guess it, no, because we're not doing the integral from 0 to infinity. But Darius.
time goes on, more and more doctors will prescribe.
And eventually, all of them will. Eventually, 100% of doctors will be prescribing this medication. That's kind of what that's telling us. If we let time go on long enough, 100% of doctors will prescribe it. Very nice. Okay, yeah, we're out of time. So we will finish the rest. When do we get to? 12? Okay. So we got some work cut out for us in front of us, but we'll finish the rest on Wednesday.
These drawing work can be uploaded to Canvas?
Yeah.